Stanford University.
We're going to begin today with the laws of motion as described by a very famous physicist. His name is Isaac. Almost 2,000 years before Isaac. Not only was it 2,000 years or 1,800 years before Newton, he got it wrong. But nevertheless, we're going to spend a little bit of time talking about Aristotle's laws of motion, or Aristotle's law of motion. Now, Aristotle didn't know how to write equations, so he didn't write equations, but he used words to describe motion. The reason he got it wrong is because he lived in a world dominated by friction. In a world dominated by friction, if you apply forces to objects, and then there's a force, and you stop the force, the object stops. The object only moves while there's a force being applied to it. The heavier the object is, Aristotle knew this, he was described it. You know, the heavier the object, the harder you have to push it to give it a certain velocity. And you also know the harder you push it, the faster it goes. So Aristotle believed that the connection between forces and motion were that the velocity of an object is proportional to the force that you put on it, not the acceleration. He thought that velocity was the natural consequence of force. It's quite clear that Aristotle, as I said in the notes, had never gone ice skating. Had he gone ice skating, he would have realized that it takes force to change motion, to stop an object. You can't stop without force being exerted. You can't get started without force being exerted. So he would have known that there was something wrong with his law of motion that said that force was proportional to velocity. But nevertheless, it's an interesting law to study a little bit and to see if we can find anything wrong with it from the point of view of things we've already discussed. And one of the things we've already discussed was the reversibility of laws of physics. Reversibility meaning that you don't lose information, that you can recoup the past as well as the future in the laws of physics. We'll see what Aristotle's laws have to say about that. It's not completely definitive. You'll see what I mean, but it goes in the wrong direction from the point of view of reversibility. Okay, so let's think about Aristotle's hypothesis. Aristotle's hypothesis was that something called force, and of course he didn't measure forces accurately. He probably didn't even have a good definition of force, but I doubt that he even used the word force. What's the Greek word for force? Anybody know? I don't know.
Dynamism. Dynamism.
Dynamism. I don't know if you use that a lot.
Like dynamo.
Okay.
Dynamics.
Dynam? With V?
Dynamis. That's where the word dynamo comes from.
Okay. But in any case, let's put some words in his mouth. Force is equal to mass times velocity. Wrong equation. Don't write it down. Well, you can write it down. Don't memorize it. Let's see if we can use it a little bit quantitatively to find out what happens. I simply want to explain in what sense this is a law of motion, and in what sense it fails one of the tests that we've already proposed for laws of motion. All right, velocity, we can write this as a vector equation. Aristotle might have written that as a vector equation, force proportional to velocity, but let's just think about the one-dimensional axis, and of course velocity is what we call x dot. mf equals x dot. And just to illustrate, let's go to our stroboscopic world where we break up time into little intervals, into little very small intervals, each interval of size epsilon. So we break up the time axis, here's the time axis, here's the time axis over here. We break it up into little intervals, each interval of size epsilon. Epsilon is a standard term for a small number. And then x dot, which means the time derivative of x, is approximately equal to, actually I think I called it delta. No, I can't remember that. I called it delta, or I think delta. Delta, a little difference of time. And what is x dot? X dot is x at time t plus delta minus x at time t divided by epsilon, delta. Of course, the real derivative, the genuine derivative, is a limit, but let's not take the limit, let's just write it this way. Alright, so let's erase this, and here's Aristotle's force law, here's Aristotle's law of motion, and let's suppose that we also prescribe the force, in other words, we exert a known force which is itself a known function of time, for example. Alright, so what does this equation say? We can solve the equation very easily for x at t plus delta. Let's do that here. Let's see, we multiply by delta, divide by m, multiply by delta, divide by n, so we have f at time t times delta divided by n equals x of t plus delta minus x of t. Let's add x of t to both sides. X of t equals x of t plus delta. So you see where this is going. This is the sort of law of physics which is telling you where the particle is, where the particle is at time t plus delta if you know where it is at time t. Exactly the same kind of thing as when we talk about coins and so forth. If you know what it's doing at an instant, and you know the law of motion, or you know the law of dynamics, or nature, or whatever, then you know where it will be at the next instant. So this is a special case of law of physics. What would it say if there was no force? If there was no force, there is no velocity, so the object stands still. You can predict the future, it just sits there, it doesn't do anything. You can also predict the past, it just sits there, it doesn't do anything. That's Aristotle. Now let's work out an example or two. In fact, I think I'll work out one example. This is slightly different, not knowing the force as a function of time, but rather knowing the force as a function of position. Here's our particle moving on the x-axis, and let's assume that it is governed by a force which depends on where it is. In fact, let's do what we would have done if it was a harmonic oscillator, if it was a spring. Then, it's an equilibrium position that we can call x of 0. And what is the force if we displace the object away from the origin? If it were a spring, just an ordinary spring, we would say the force pulls us back, and moreover, it's proportional to the distance that we displace things. We would write the force is equal to minus k times x, so we can call k the spring constant, and force is proportional to displacement. Let's see what that would do in Aristotle's equations. We can either, let's work with the discrete form, like so. All right, instead of writing f of t now, where right? Instead of writing f of t, let's write down minus k times x at time t. All right, the force is now minus kx, and so I wrote that in here. All Or we can write that this is equal to x of t times 1 minus k delta over m, is that correct? That's equal to x at t plus delta. All right, what does this equation say? It also allows you to predict the future. If you know the position at any time, it'll tell you to multiply the x-coordinate by a number slightly less than 1. Think of delta as a small number. Think of delta as small. So this is small here. 1 minus a small number is a number slightly less than 1. So each interval of time, what happens to the position is it gets diminished by the same common factor. So if it was over here to start with, it would be over here next, over here next, and each time x diminishes by the same constant factor. What's happening is that the particle is just exponentially moving toward the origin. You can also work this out. You can work this out without doing the discrete form. You can do the continuous form. Instead of writing this complicated thing here, we would just write that dx by dt, velocity times mass, is equal to k times minus x. And then we would solve this equation. Solve this equation, k over m times x. What's the solution of the equation? Well, what function has a property that its derivative is proportional to itself? The exponential function. All right, so the solution to this is x is equal to any constant times e to the minus k over m t. It's just another form of an exponential decrease. What happens to x? It goes to 0 at late times. Where's the starting point? Let's say at t equals 0. It started out at t equals 0. A is the value of x at t equals 0, so we can, instead of calling it a, we could just call it x at this starting point, x of 0. And all that happens is, if this is the origin, and we displace it and let it go, it always moves back to the origin, getting slower and slower and slower as it goes back. It exponentially decreases. Well, wait a minute, that sounds almost like you can't predict the past. You can sure predict the future. The future is that wherever you are, you'll exponentially move toward the origin. But can you predict the past? All right, so in what sense can't you? Here's the sense. If I displace this thing, tiny infinitesimal amount, too much, too small to even be detectable, and run it backward, where does it go to? All trajectories aim in and go to the origin. So from the fact that at a future time, some future time, the particle is just sitting at the origin practically still, you can't tell where it came from. Now, of course, if you had infinite accuracy, you could. But with a finite accuracy, a finite ability to tell exactly where it is, where it's moving, you can't tell where it came from, because wherever it came from, it went to the same place. It went to the same place and stopped. It just stopped. So if we mean by ability to predict the past is that that not all configurations ultimately run to the same thing, but that initial distinctions get preserved in some form, this is looking a little bit suspicious. It's a little bit suspicious because it looks like different starting points inevitably lead to, within any arbitrary accuracy, to the same final configuration which just sits there. So you couldn't, in that sense, in practice, predict the past with it. This is not what happens with Newton's equations. We'll illustrate some examples with Newton's equations. With Newton's equations, the simple systems like this, they do not run all to the same point. But if you start with different configurations, measurably different, you'll end up with measurably different configurations. So Aristotle's law, apart from being experimentally incorrect, is also irreversible. Now you can't criticize Aristotle for writing down the irreversible law. You say, what do I care? You're the guy who said it has to be reversible, not me. And of course, he was right for the practical situations that he's talking about. This is irreversible. You can't tell where it came from the fact that it's sitting there, period. We know that we know in what sense Aristotle was completely wrong. What he was wrong about when he said that force is proportional to velocity was that force is really responsible for the change of motion. Let's see, yeah, friction. What is friction? Friction is itself a force. When you say that the velocity of this is proportional, the velocity of this is proportional to the force, what's really going on, of course, is there are at least two forces that apply to this object here. One my finger, and one the force of friction. The force of friction is ultimately a microscopic force with molecular motions and all kinds of things which are much too complicated to deal with. So we just call it friction, but it's really a balance of force. It's not that the force is necessary to make velocity, it's just that one force is necessary to overcome the other force. So we all understand that, it's nothing new. And moreover, we probably also all understand in what way Newton's laws are different. So let's talk about Newton's laws, and then let's discuss their predictability in the same sense. Are they predictable into the past, and are they predictable into the future? Okay, so what's Newton's corresponding law? Newton's corresponding law is F equals ma. Before I talk about that, let's just talk very briefly for about 1 second about something called inertial reference frames. When I learned about inertial reference frames when I was in college, I got very confused. I could not tell what the professor was talking about. On the one hand, he said, Newton's laws are only true in an inertial reference frame. And then the next breath, he said, what an inertial reference frame is it's a frame in which Newton's laws are true. Well, it's slightly circular. I couldn't. It took me some time to work my way out of that puzzle. But let's, for the moment, just say it a different way. A frame of reference, of course, means a set of rods and clocks. And those rods and clocks may be moving, or they may be standing still. They may be a frame of reference on a railroad train. It may be standing still. We're not doing relativity now, but we can talk about moving frames, rotating frames, all kinds of frames of reference. There's a subset of those frames of reference where if we label particles by the coordinates associated with the rods, we label time by the clocks and so forth, that whatever Newton's laws are, Newton's laws will be true in those frames of reference. Other frames of reference, which are rotating relative to those frames of reference, or accelerating relative to those frames of reference, will not be good frames of reference in which Newton's laws are true. The law of physics is not that Newton's laws are true in inertial frames, and inertial frames are where Newton's laws of physics, Newton's laws are correct. The law of physics are that there exist inertial frames. There exist inertial reference frames far from gravitating objects, far from any forces, or even when you're near forces, frames of reference in which Newton's laws are true. We'll now write down what Newton's laws are, and then later on, we'll try to work out from Newton's laws what they would look like in other frames of reference. So the law of physics is that there exist frames of reference in which Newton's laws are true. Newton's laws are, we haven't defined force yet, we haven't defined mass yet, we're going to do so in a little while, but this is also equal to x double dot. Yeah, let's take a few moments and think about what this means, how you would check it, how you would experimentally verify it. The problem is, again, a little bit of a chicken and egg situation. We've defined acceleration, second time derivative of position, and position we described in terms of meter sticks laid out in various ways. This is well defined. We know what acceleration is, and presumably we know what time is, so we can take a second time derivative. How do we get started? Again, it's chicken and egg definition versus law. Force, that's mass times acceleration. Well, what's mass? Force divided by acceleration. That's not helpful. So we have to, it's exactly what is it that this law of nature is saying. So let me give you an example of how you would check it. You have a block of an object, weighs 1 kilogram, or its mass is 1 kilogram. By saying its mass is a 1 kilogram mass, it means if you hold it in your hand and you hold the kilogram mass that's located in Paris somewhere, in some isolated place, if you hold both of them in your hand, they'll feel the same. Or if you put them on a seesaw or on a teeter totter, they'll balance. So that's an experimental test of whether a thing weighs 1 kilogram. So this is a 1 kilogram mass, or some well-known defined mass. And now we hook it to a spring balance. The spring balance has a spring on it, let's see, a spring on it, and the spring over here is hooked to a hook over here. It's also hooked at this end to the mass, and we pull on here, and that stretches the spring a little bit, and of course in the process exerts a force on the mass here. And what happens when you exert the force on the mass? This is being done in free space, it's not being done on the tabletop, it's being done far from anything which can cause friction. What happens is, of course, the mass accelerates. That's an observed fact. Right, so that's an observed fact. And I can also give a meaning to a unit of force by saying the spring here stretches a certain definite amount. When I pull on it, let's call that amount epsilon. When the spring stretches amount epsilon, I will call that one unit of force, and of course I will find that it accelerates. Now how can I exert 2 units of force? How can I know that I'm exerting 2 units of force? What do I have to do?
2 springs.
2 springs. Right. Don't stretch the spring twice as far. Why not? Because you can't be sure that the spring is a truly idealized spring. The spring is made of atoms and so forth. If you stretch it too much, it will break. It's real springs are nonlinear. Don't do it that way. Just put another spring on. Stretch it the same amount as before, and you're now exerting twice the force on it. 2 units of exactly the same force. What happens? It accelerates twice as fast. Double the acceleration. Put 3 springs, it accelerates 3 times the acceleration. So we found out that the acceleration is proportional to the force. Acceleration is proportional to the force. So far, we haven't checked the mass side of it. All right, so now we do something different. We go back to 1 unit of force with one spring balance there, and now take 2 1 kilogram masses and hook them together and try to pull it. What happens? It again accelerates, but it accelerates with half the acceleration that it had before. Put 3 units of mass on, it accelerates 3 times slower. So by experiments like this, we could check. We could check, not only check, but at the same time we would be defining and checking this law that the acceleration is proportional to the force and inversely proportional to the mass. So that's what we mean by it. And now there's no question anymore of what's defined and what's a law of physics. We've defined force, we've defined mass, at least we've defined what means to double the force, to double the mass, and so forth. And we can check this law of physics, and of course it's true. Now, is it predictive? Predictive, I will mean the following. If you know where the object, I tend to call these things particles, but it doesn't mean that they're elementary particles, they're just little objects. if you know where it is at one instant of time, and you know the mass and you know the force on it, do you know where it is the next instant of time? Is it predictive in the same sense that Aristotle's law was? And so we can go through this, and it's a little bit interesting to go through it in detail. What does x double dot mean? It means the time derivative of the velocity. The velocity is the time derivative of the position. So let's write that down. What is velocity? It's x of t plus delta minus x of t divided by delta, right? That's the velocity at time t, or somewhere between t and t plus delta. That's velocity. I want to, the second derivative, you'll have to take the difference of the velocity at two neighboring times. So let's subtract the velocity of the neighboring instant time just before x of t minus x of t minus delta divided by delta. This is the velocity somewhere between t and t plus delta. Here's the velocity 1 unit back earlier. And what is the acceleration yet? No, I have to divide it by another delta. Another delta because we want to take the difference of velocities and divide it by delta. And that's the acceleration. Well, that's the discrete approximation to the acceleration. It's also equal to x of t plus delta plus x of t minus delta minus twice x of t divided by delta squared. I'll put the delta squared in a moment. We want to write that the mass, we're going to multiply by the mass, and set it equal to the force. All right, so we can write then force over mass. And now I think I left out the delta squared, so let's put it in over here, delta squared. That's our law of motion. And now let's solve for x of t plus delta. X of t plus delta then is equal to x of t plus delta is equal to this, so I transpose to the right, plus twice x of t, and then minus x of t minus delta. I just move this to the other side of the equation. Did everybody read that? We're sloppy today.
Could you maybe move your
Yeah.
jumper?
Hmm?
Could you move your coat or jacket?
Oh, yes. Yeah, but I'm also going to move the symbols. Let's see, I think it was plus 2x of t minus x of t minus delta. Do I have it right?
Yeah.
That's equal to x of t plus delta. Well, now I have a formula that tells me where the particle will be next, but I need to know more than just where it is at an instant of time. I also need to know where it was at a previous instant of time. It's not enough to know where the particle is to know where it will be next. You also have to know where it was in the past. So it looks like these are not predictive laws of physics. They don't satisfy the rule that if you know everything about the system that you can know, then you can know what's next. But wait, that's not really right, because, again, chicken and egg story. What do you mean by saying you know everything that there is to know about the system? You mean everything you need to know in order to predict the future. That's, if you like, that's the definition of what it means to know everything about the system. Everything you need to know to predict the future. So, what we learned is we have to know two pieces of information, both where the particle is and where it was one instant before. Equivalently, if we think about the real derivatives and differential form of the equation, where it really says, this is something, again, you can know very well, that in order to use Newton's equations to be predictive, you have to know not only where the particle is to begin with, the initial condition, or call it the initial condition, you have to know both the position and the velocity. The velocity tells you where it was a moment ago, the position tells you where it is now. So if you know these two things, then you can predict the future using Newton's equations. That's what we learned by that little example, by the discrete example. This is what you need to know, and basic idea now is that the we won't call it configuration space. The space of what is important, the space of what's important consists of two things. All right, let me write Newton's equations slightly differently. Let's try to investigate the predictive power of them now using the fact that we need to know both of these things. Let's invent a new concept called momentum. Momentum is by definition mass times velocity. Definition, mass times velocity. Mass is always assumed to be constant. The mass of an object in Newton's theory is always assumed to be constant. And the mass of a thing can change, of course. If this pen is moving along, the cap can fall off and the mass of the pen decreases. But apart from losing pieces of an object, the total mass hasn't changed. The total mass has stayed the same. In Newton's physics, total mass of the system remains constant. All right. So the symbol for momentum is P, and it is of course also a vector. Since x dot is really v, is really velocity. All right, so now let's rewrite Newton's equations. Of course, acceleration. It's obvious from this equation here that we can rewrite it as force equals, forget the mass, just the time derivative of the momentum. The time derivative of the momentum is the mass times the time derivative of the velocity, and that's the acceleration. So this is ma. That's the first of the two Newton equations. You'll see in a moment why I say there are two Newton equations. F is equal to the time derivative of momentum, and the other equation is that momentum is equal to the time derivative of position times mass. Think of this now as two equations that are two equations, differential equations, for x and for p. Think of them as two separate variables. Of course, we thought of this as a definition, but now don't think of it as a definition. Just think of it as an equation. What does it say? Is it predictive? Let's see in what sense it's predictive. So we can rewrite this. F is equal to P of P plus delta minus P of P divided by delta, or we can solve for P of T plus delta in terms of P of T. And the other equation is that P is equal to X of T plus delta minus X of T divided by delta. So if we know X and T to be zero, then we can proceed to solve and be predictive. One equation tells you how X changes, the little incremental change in X if you know P, and the other equation tells you how P changes if you know the force on the system. So the only new thing that we have to add then is that the space of initial conditions is not, as it was in Aristotle's formulation, just the space of possible positions, it's the space of position and momentum. You can use velocity if you like. It's just conditional to use momentum. And so we specify the state of a particle, one-dimensional particle, moving on a one-dimensional axis by specifying a location x and a momentum p. Let's just put a picture, let's see what it means. We're assuming we know the force. We're assuming that somebody has given us the force on the object as a function of time. Right? So if we know the force, the first equation tells us how P changes, a small increment of time, P changes a little bit from this equation to the other equation that tells us if we know P, we know how much X moves. So we move from here to here. Once we move from there to there, we can just do it over and over again. The next step, we're at a new value of P. All right, so that tells us where X will be next. And we're at a new value of the force, that tells us where X will be. And so we build up a trajectory completely predictive. Completely predictive. That's Newton's equations, and you should think of Newton's equations in this language as being two first-order equations. First-order equations mean only first-time derivatives, but for two variables. Instead of one second-order equation, two first-order equations, and one sees that it's completely predictive. Okay, the space of positions and components of momentum has a name. It's called phase space. It's a very important concept in all of physics, phase space. It's on the one hand, space of initial conditions, what you have to know to predict the future. In this case, it's just a single particle. And it's positions and velocity, the positions and momentum. Yes.
If it's, in your previous example, f is actually a function of x, then isn't it a more complicated kind of...
Yes. Right. So if this happens to be a function of x, rather than a known function of time, if the force depends on where you are, still it's true that if you know x and p at an instant, this equation will tell you where p will be next, and this equation will tell you where x will be next. You can use it to update the initial condition, and then do it again and again and again. So yes, it's okay, let's take an example now, analogous to the case that Aristotle did to describe the motion of a spring when he pulled it and let it go. And what happened with Aristotle? He pulled it, he let it go, and then it just exponentially drifted to the origin and stopped. Remember? Okay. And therefore, he was unable to predict where it came from after a period of time. It just comes to rest in the story. Let's do the same analogous thing for the Newtonian version. There's no particular reason at the moment to think of it as two separate equations. We can, but let's think of it as just an equation. F, mass, times acceleration, x double dot, is equal to minus kx. That's the same case that Aristotle did, except Aristotle wrote x dot instead of x double dot. Newton writes x double dot, second time derivative. And let's solve that equation. Rather than solve it pretty well, let's simplify it first. Let's simplify it so we're not carrying around a bunch of constants. Let's set n equal to 1 and k equal to 1. Okay, just the point we're making here is not to carry the constants around, it's to understand the logic. So here's our equation, x double dot. Let's compare it with x dot. The solution of this was x is equal to a constant, x of 0, times e to the minus t. After a long time, it just drifts to the origin and stops. What about this equation? We're looking for a function whose second time derivative is the same as itself, except with a minus sign. All right? I don't know if we all know the solution to such an equation. Some of us know the solution to such an equation, but I will tell you. They will satisfy equations like this are sines and cosines. In fact, we just say sines or cosines, doesn't matter. Sines and cosines. If you differentiate a sine, you get minus the cosine. If you differentiate the cosine, you get the sine. So differentiating sine twice, you get minus cosine, and then back to minus sine. So the general solution of this equation is that x is equal to a constant times sine of t, let's call it minus t naught. We could use cosine, it doesn't matter, you can use either cosine or sine. Let's use cosine. You know, the cosine of any angle is also the sine of some other angle, isn't it? Right, so it's just a shift of what I call t naught. Let's use cosine. Cosine of t minus t naught. Okay. When is the velocity equal to 0? Can anybody tell from this equation when the velocity is equal to 0?
T minus T naught equals pi over 2. Oh, no, that's what x equals 0.
Not quite.
You're
You're on the right track.
I've got the
T
derivative.
minus t naught is equal to 0.
Yeah.
Right. The derivative of cosine is 0 when the argument of the cosine is 0. So the velocity is 0 when t is equal to t naught. Well, that tells us. Right, so t naught then just tells us at what point the velocity is equal to 0, and c tells us the amplitude of the vibration, how big the vibration is. That's the only solutions that there are to this equation. Constant over here, two constants, c and t naught, and that's the most general solution. Now, what kind of motion is this? First of all, it doesn't come to rest. Well, it may stop momentarily at the maximum of the cosine, but it won't come to rest. It will keep oscillating. In fact, when it comes to rest, is at the maximum value of the expression, and when it gets to the origin, it's when the velocity is maximum. So it's exchanging back and forth velocity for amplitude. All right, but it never comes to rest, and so there's no danger that it will do this irreversible thing of losing track of where the hell it started. Well, we can do a little better. We can plot the motion a little better. Let's calculate the velocity. This is x. What about x dot? All we have to do is differentiate this, right? What's the derivative of it? Minus c sine of t minus t naught. Let's take, this is also the momentum, because I set the mass equal to 1. So the position is cosine of t minus t naught, and the momentum is sine of t minus t naught. Consider this thing moving in phase space. Here's p, and here's x. X and p are both oscillating, but there's something else we can say. We can say that x squared plus p squared is constant. In fact, what is it equal to? It's equal to c squared. X squared plus p squared. Use sine squared plus cosine squared is 1. X squared plus p squared is equal to c squared. So first of all, we see that in the phase space, the point describing the configuration in phase space moves on a circle of radius c. Now c is an arbitrary number. We can have big circles, small circles, and so forth. Smaller circle, small circle. These are different initial conditions. The big circles are ones where we pull the spring far and then let it go, and oscillate it back and forth. The small circles are just ones where we displace it a little bit, still oscillating back and forth. In fact, the amount of time that it takes to go all the ways around is the same, independent of c. It takes an amount of time 2 pi to go all the ways around, and all of the points in phase space here move the same way. They may start at different locations, but they just move around in circles. That is not only predictable to the future, but it's predictable to the past. If you know where the system is in phase space at any given instant of time, where will it be next? After an amount of time t, it will have moved to an angle. The angle of this difference is just a small change in time. So the whole thing just goes around in a circle forever and ever, all points in the phase space just moving like clockwork. And there's no danger, no possibility of losing track or of not being able to predict the future of the past. In fact, the past and the future are very much alike. Only difference is you wind counterclockwise for one, and clockwise for the other. So, this is yes.
So instead of double derivative of x equal to minus x, if you make it equal to single derivative of minus x, then don't we lose the predictability?
No. We'll come back to that one. No, we don't. There's a theorem that we're eventually going to prove, but we'll come back to it. In what sense? What? Come back to that. Okay, let's see. What else should we do with this? I think not much for the moment. Well, let's do one more.
Question. Quick question. One of the basic premises of your model is things should be reversible.
Well, we're testing out to see what things are reversible or not reversible.
Yeah, I think, given the axiomatic system you described last week, that's by definition the case, but
Yeah.
why should we believe that that is true of physics in general?
We try it out and see how it works. That's all I can say. Why does it have to be true? I think all we can do is build up the laws of physics as we know them, look at the common features, and of course they come from experiment. We look at the common features, we try to derive principles from the common features we call principles, and we ask what principles are there. Now, I'm of course teaching a course that starts from the most elementary physics and goes to the most advanced. The logic really goes the other way. The real logic goes the other way. The most advanced thing we're going to study, well, whatever it may be, let's call it quantum field theory or something. Quantum field theory is really the bedrock foundation of what physics is about. And from it, by a series of approximations, slow motion, heavy objects, various approximations, you derive Newton's equations. So really, in fact, the logic goes the other way. But when I'm teaching it, I can't teach it that way. So we start with some simple principles, which I know in the end are going to be the ones which do derive from quantum field theory. I know that. I know that quantum field theory works this way. But for our present purposes, I think we have to postulate some things. And I'm using my personal hindsight and trying to convey to you what in the future you will see as a set of principles that derive from a small number of assumptions. But we can't do it all at once. Okay.
So is that fair to say that then reversibility wasn't something Newton understood to be important?
That's good. I don't know. I don't know. It's a good question. But he did understand the principle of inertia. He certainly understood the principle of inertia, that it doesn't take force to make something move, and it takes force to make something change its state of motion. Okay, so I don't know to what extent Newton was aware of the reversibility. Now, I will also tell you something else. You can see the reversibility in another form. Let's take this equation. Well, let's first start with Aristotle. The x by dt is equal to f of x. What happens to this equation if you change the sign of time? If you invent a new time variable, let's call it capital T equals minus little t. What happens to the equation? What happens to this side? It changes sign. What happens to this side? It doesn't change sign. By definition, when I say this equation, I'm going to take this equation and change the sign of time. The equation does not stay the same. It is not the same equation. The meaning of that is that if you took a movie of a process and you ran it backward, it would not be a solution to the same equations. Not too surprising, if you take Aristotle's force, Aristotle's law, things come to rest eventually. They don't suddenly start moving according to his force, according to his principle. So, this equation is not reversible in the sense that if you change the sign of the time, the equation doesn't stay the same. What about Newton's equation? d second x by dt squared. What happens if you change the sign of time here? Nothing happens. If t goes to minus d, d squared stays the same as d squared. So does dt squared. So second time derivatives don't change sign when you change time to minus time. Another way of saying it is if an object has a certain acceleration and you take a movie of it and run the movie backward, what happens to the acceleration? Nothing. You run a movie of an acceleration backward and it is exactly the same acceleration. Whereas if you run a movie backward of a velocity, the velocity changes sign. So Newton's equations in that sense are reversible in that if you take a movie of possible motion that solves Newton's equations and run it backwards, it's another solution. You can't tell which movie was the solution of the equations and which wasn't because they both are. Whereas in Aristotle's law, they're not. Okay, so we'll come back to this. We'll talk about some more examples. The next thing we want to talk about a little bit is conservation laws. When we were talking about very simple laws of physics, namely coins and dice, we talked about conservation laws. Conservation laws were simply numbers that we got attached to a trajectory so they change. Numbers which are called being attached to a cycle. Incidentally, in this case here, it's clear that all of the motions lie on cycles. Cycles that go around and around. In a different cycle, you never jump from one to another. You never jump from one to another, so apparently there is a conservation law. However you describe it, this orbit cannot jump to this orbit, so we can ascribe to the different orbits a quantity. What was it? It was the quantity c squared, which was in fact x dot squared plus x squared. We have a name for that quantity. What's called? Energy. 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 Well, strictly speaking, there's a mass here divided by 2 and a k divided by 2. And since I set the mass in k equal to 1, then c squared, apart from a factor of 2, is the energy of the orbit. Different orbits of different radii correspond to different energies. And that's it. That's the whole story of course, the harmonic oscillator. We'll come back to it many times. This is the foundation of an awful lot of physics. But what you should have in your mind now is that the theory of the harmonic oscillator is a theory in phase space where the system simply executes circular motions in phase space of different radii corresponding to different energy. And the thing you can do is vary the energy and also vary the starting point at time t equals 0. You can start it over here, you can start it over here, you can start it over here. And that's all. That's all the only possibilities. If you project the motion onto the horizontal axis, then you're just looking at x. And what does x do? It goes back and forth and back and forth and back and forth. It's a vibrating oscillator. If you project it on the p-axis, or both axes, you notice that when x gets to its maximum, p is 0. Velocity is 0 when it gets out to the maximum, and then it swings in, and when x gets to 0, that's when it's moving with the most rapid momentum. Okay, so that's But, again, this is just an example for us for now. Okay, let's talk about momentum conservation. Oh, let's talk about Newton's first and second law. Newton's first and second law. Newton's first law is in the absence of forces, the thing moves with a constant velocity. Newton's second law is that in the presence of forces, the force is equal to the mass times the acceleration. One of these is clearly redundant. We don't really need the first law. The first law is just a special case of the second law. Second law, d second, let's call it r vector by dt squared times m equal to force. Newton's first law is if there are no forces, an object moves with constant m dv by dt, velocity, is equal to force. If the force is zero, the velocity is constant. We don't need a separate law for that. The first law and the second law are part of the law, part of just the second law. I think we're going to. Now there's Newton's third law. Let's state Newton's third law and then see what it says in some more complicated or more general sense. What it says is it's a law about the force that is exerted by one object on another and its relation to the force the other object exerts on the first. We might as well begin with an assumption that everything is made up out of particles. Let's make that assumption. Everything is made up out of point particles. Particles exert forces on each other, and the net force exerted on any one of them is the sum of all the forces due to all the others. We're making an additivity assumption that forces add as vectors. Let's say add and then add as vectors. And that forces come in pairs. The force of A on B, or the force of particle 1 on particle 2, and the force of particle 2 on particle 1. The first statement is that the force of 1 on 2 is equal and opposite to the force of 2 on 1. Alright, so this says that if 2 exerts a force on 1 pulling it that way, 1 exerts a force on 2 pulling it that way. We'd be in a very funny situation if that weren't true. Let's just imagine what would happen if that wasn't true. In particular, let's imagine that the force exerted by 1 on 2 and the force exerted by 2 on 1 were the same. Not opposite, but the same. Then it would say, then they would be both pointing in the same direction. What would happen to the system? It would just spontaneously take off. Right? Just spontaneously take off and accelerate away. Be a very nice source of energy, but maybe you might get away. But that doesn't happen. From experience, we know that there's no free lunch, there's no way to get the thing to accelerate without exerting the force on it, and so this can't be right. It's not right. Newton's third law begins by saying the forces between two objects. We can write that in the following way. Let's suppose we label the particles I. I goes from 1 to however many particles there are. The force of I, the force on I, due to J. Okay, so let's remember what this means. This is the force exerted by J on I. It won't make too much of a mistake if you get the notation backward. Just be consistent about it. What does this law say? It says that the force exerted by J on I is equal to minus the force exerted by I on J. They're equal and opposite. All right, let's derive the consequences. Oh, before we do that, let me state the rest of it. We have two particles over here exerting forces on each other. here has equal and opposite forces. Let's say the force on the force on 2 due to 1, let's suppose is in that direction and it's that big. The force on 1 due to 2, let's suppose is this way. Are they equal and opposite? Yeah, they're equal and opposite. What does this thing start to do if you just leave it alone? Faster and faster and faster, because this one keeps exerting a force on this one. That, picks off like a propeller. Again, there are no free lunches. We can't get energy out of nothing. There are no perpetual motion machines. This must be something wrong with this. What is the alternative? The alternative is that the forces are along the lines of centers, like that. Not only equal and opposite, but pointing toward or away from each other. Now, can this thing take off? Well, it can't expand or contract because there's a rod, a strong steel rod in between them. It can't do anything. It won't start rotating. It won't take off with a net motion because the forces are opposite to each other. It won't do anything except maybe squeeze the rod a little bit or stretch the rod a little bit depending on which way the force is. Yes, this is the way forces really work. So this is true. And the other one I have a little difficulty writing as an equation, a long line of centers. A long line of centers. All forces are along the lines of centers. That's Newton's third law, stated in modern terms. Along the line of centers we'll come to, basically what it has to do with is conservation of angular momentum. We'll come to that. But the equal and opposite has to do with the conservation of momentum itself. So let's see how that works. Supposing we have a whole bunch of particles, let's label them I, and they satisfy equations of the following type. It's a closed system. There's nothing else in the system but these particles. No external forces from other objects, only the forces of the particles on each other. We can write that the mass of the ith particle times the acceleration of the ith particle. Let's use vector notation now. Position vector by dt squared. The ith particle is equal to the sum over all the other particles. Sum over all the other particles, j not equal to I. Particles don't exert forces on themselves, so that the other things exert forces on them. J not equal to I of the force exerted by J on I. Sum taking into account all the particles. This is the equation of motion for the ith particle, if you like. In fact, let's write it differently. This is mass times the derivative of the velocity, right? Derivative of the velocity vector. Or equivalently, it's just the derivative of the momentum of the ith particle is equal to sum j not equal to I, Fij vector. Force is time derivative of momentum. Each particle has a force on it equal to all the others. Now let's, and of course there's an equation for each I, right? 1, 2, 3, 4, up to however many particles there are. Let's add all of the equations for all the particles. What does that give us on the left? It gives us the time derivative of the sum of all the momentum. Right, so on the left side here, we get d by dt of the total momentum, let's just call it total momentum of all the particles. What about on this side? On this side, we have to now sum over I and j. We took this equation and summed it over all of i's. That gives us the sum over both I and j of Fij. Well, what do we get now on the right-hand side? We get 0. We get 0 because each pair of particles is counted twice. One for the force of J on I and one for the force of Y on J. So when we add up all of the forces of all the particles on each other, they add up to 0 because they come in equal and opposite matched pairs. So the result is, from Newton's third law, that this is equal to 0. Well, what does that say? That says that total momentum is conserved. So that's our first conservation law. Total momentum is conserved as a consequence of Newton's principles. Now, again, you can ask, why should Newton's principles be right? And I can tell you that in modern terms, the conservation of momentum is more fundamental than Newton's expression of his laws. And you can read it the other way. If momentum is conserved, then it must say that for a pair of particles, the forces must be in the opposite directions, equal and opposite. So you can read it, you can either think of the derivation going one way or the other. But as I said, since we're following some a little bit historically, Newton's law implies conservation of momentum. So that's our first conservation law. After I've had a bit to nourish myself, and you have had a chance to do whatever it is that you like to do, and if you have any break, we'll get back to energy. Or we'll get to energy. We'll get to energy. We proved momentum conservation from Newton's third law. Let's prove energy conservation from Newton's equations, but we're going to do it first for a particle in only one dimension. A single particle in one dimension and we'll assume there's some sort of force on it. The only assumption is that the force depends only on where the particle is. In other words, the force depends on x. Let's write that by saying force depends on x. And in particular, the force does not depend on time. Well, it depends on time implicitly. Where the particle is may depend on time. But no matter what time you look at the particle, if it is at position x, it has force f of x on it. So we would call this a time-independent force, but it doesn't mean that the force itself is time-independent. It means that the force is only time-dependent through the fact that the position may be time-dependent. Force only depends on the position. All right. We've already done an example. Kx or minus kx was an example for the spring. And now let's write Newton's equation for the motion along a line. Well, let's not. Let's prove energy conservation by defining the energy and then checking whether it's conserved as a consequence of Newton's law. We could go the other way. We could use Newton's law to try to figure out what the energy was, but it's cheaper and simpler to go the other way. Define the energy and then check that it's conserved. All right, the energy of a particle consists, wait, back a step. In one dimension, you can always think of any function as being the derivative of some other function. Given a function f of x, you can always write that that function is the derivative. And I am assuming, of course, the functions are continuous. They don't have wild, crazy behavior. Then you can always find a thing called v such that f of x is dv by dx with a minus sign. The minus sign is an arbitrary convention, and v is some function of x. It's called the potential energy. How do you construct v? Anybody have a good suggestion for how, if I know f, how I find v? Integrate. Integrate. If I integrate both sides of this equation, integral f of x dx will be minus v of x, where this means indefinite integral, or integration from some point to an arbitrary point. All right, so you just undo derivatives by integrating, you undo integrations by differentiating. And so if, assuming, of course, that the function f of x is nicely enough behaved that you can make an integral out of it, then there is always a v of x such that f of x is the derivative of v of x, and throw in a minus sign for convention, for standard definition. Let me write it again. Now, first of all, is there a picture in your mind that you should have that goes with this? Yeah, think of the following picture. That your particle is moving along the x-axis, but it's on a series of hills of different altitude. The altitude is roughly v. So it's moving along x, but it's on hills that go up and down and so forth. The higher the hill is, or the higher the altitude, the larger the potential energy. So the altitude here is v of x, or is v. Plot v this way. If you put a particle on a hill over here, there's going to be a force on it, an effective force along the x-axis. It's going to accelerate along the x-axis. Which way is it going to accelerate if it's over here? Back. If it's over here, forward. All right. So it's going to accelerate toward lower altitude. That's why the minus sign is here, or that's the way to think about the minus sign. It accelerates toward lower v. Moreover, it accelerates at a rate which is proportional to the slope here. The steeper the slope, the larger the force is going to be. I mean, this is just a matter of common experience. And so that's the way you should picture this. A sort of terrain where the height of the terrain is v, and there is a force at every point pushing you towards smaller v. That's what the minus sign is. And dv dx is just the slope of the hill. At the top of the hill here, there's no force. That's because dv dx is 0. At the bottom of the hill is no force, and the force is maximum where it's steepest. That's what this means. Okay, now, so we really haven't made any real assumption. The only assumption we've made is that f is smooth, is a nice enoughly behaved function that we can integrate it and find v of x. Okay, let's prove the following simple theorem. That if we take 1/2 the mass times the velocity, I don't want to call it velocity because if I do, we'll get it confused with v over here. This is not the velocity. Let's give it a capital V. Capital V. It's called the potential energy, of course. All right. So we'll take a quantity which is 1/2 mv squared. Now v is the velocity in this formula, small v, plus v of x. This is a function of the velocity and the position. It's called the energy. It's called the total energy, and we're going to prove that it's conserved. Why do I call it the energy? I call it the energy because it's conserved. That's the only thing you need to know about energy. It's a conserved quantity. Yeah, question? No. Okay. So let's see if we can prove that. And of course, this is just x dot squared. So we've made no assumptions up to this point, except we've defined a quantity, which we can call E. This, of course, is the kinetic energy, usually labeled T. I don't know what T stands for. I don't know what it stands for. And this is just called V, the potential energy. Why V? Has something to do with voltage. Why T? I really don't know. So T plus V. And let's prove that T plus V is conserved, that it doesn't change with time. Whatever it is, whatever you set it equal to in the beginning, it doesn't change with time. Now, first of all, we can look at this picture and get some perspective on it. If we start at some point with some velocity, or whatever, however, and we roll down the hill, the potential energy will decrease. Of course, when rolling down the hill, the speed or the velocity will increase. So there'll be, at least qualitatively, a trade-off. As the potential energy decreases, the kinetic energy will increase. As you roll over to here, you start up here, the potential energy will start increasing, but it will slow down to compensate, and the kinetic energy will decrease. All right, that's a picture, that's something you can keep in your head, but we really want to prove that this quantity does not change with time. What's the input? The input is Newton's laws. So let's write Newton's law right over here. The rest of Newton's laws are that this is equal to the mass times the acceleration, x double dot. This is the form of Newton's laws that we're going to use. And we're going to prove from this that the total energy is conserved. Okay, what do we need to do to check it? We just take its time derivative. If you want to see that a thing is conserved, what you really want to do is prove that its time derivative is 0. So let's take the time derivative of first this term over here. Again, mass is always thought of as a constant, not to be changed. So to take the time derivative of this, we get 1/2 m. And what's the time derivative of x dot squared? First of all, the time derivative of anything squared is twice the thing times the time derivative of the thing which was squared. All right? So this is going to be twice 1/2 m. We're going to have a 2 from taking the derivative of a square. This is a 2. There's an x dot and then an x double dot. Does everybody see that? We take x dot squared. That gives us an x dot and an x double dot and a 2. First thing. Now, what about the time derivative of v of x? I said that v of x doesn't depend on time. But of course it does, because x depends on time. The position depends on time. So how do we find the time derivative of v? We're interested in dv by dt. But v only depends on x. So all we have to do is multiply and divide by dx. The ratio of dv to dt is dv by dx, dx by dt. It's as simple as that. But what is dx by dt? Just x dot, right? And what is this all equal to? It's equal to dE by dt. Notice that both sides of the equation have an x dot in them. The factors of 2 cancel, and this gives us m x double dot. Everything has an x dot multiplying it, here and here, plus dv by dx. That's equal to dE by dt, right? Everybody happy? But what is this? This is mass times acceleration, and this is minus the force. So Newton's equations say that this is equal to 0. And therefore, the energy is conserved. Right, so this is a mathematical derivation of the precise quantitative sense in which kinetic energy increases when potential energy decreases, and so forth. Right. And we didn't have to pay the price of any assumption other than that we could integrate the force to find the potential energy. Okay. Now, what happens when there are more dimensions of space? Let's take the case of, stay with one particle for a moment, but let's take more dimensions of space. When there are more dimensions of space, we could call them x, y, and z, or we could call them x1, x2, and x3. I'll call them x1, x2, and x3. Then the question is, we want to write vector equations, and our vector equations have components, and the components are going to read f sub I being x, y, or z, or 1, 2, or 3, f sub I of x in component form is equal to m xi double dot. The full vector equation we could write, we know how to write the vector equation. All right, so for each one of the components, that's true. The question is, what can we say about f in particular? Can we say that f is related to a derivative of a potential energy? What I would like to write is the analog of this equation over here, but now x in general depends on all of the components of position. It's not just that f depends on the ith component of force depends only on the ith component of position. In general, the force will depend on where you are, in other words, all of the components of position. So this x in here stands for x, y, and z. All right, or however many dimensions of space there are. Is it in general true that if I take, let's say in this case, 3 functions of position, is it generally true that they're related to derivatives? No, it's not, but let's write down what we might have liked to write down. We might have liked to write down that f sub I of x is equal to minus the derivative, the partial derivative of v of x with respect to xi. In other words, I assume you know what a partial derivative is, that wherever you are, the component of force is proportional to the rate of change of potential energy along that particular direction. For example, here's the x-plane. Here's the x-plane. At every point on this plane, v has some value. We could describe it by a contour map. These are the level surfaces of v. V might decrease as we go from here to here to here to here. And the partial derivatives of v are just another way of speaking about the rates of change as we move either along the x-axis or the y-axis. So v changes because x and y changes. Is it true, question, that if I take any set of functions, f1, 2, and 3 for the 3 directions of space, any 3 functions of position, is there always a v whose derivatives, whose partial derivatives, give you that f sub I? And the answer is no. It's clear why. There's only one function f of x, and that's not enough structure to give you 3 independent, general independent functions f sub I. Just not enough. All right? So it would seem on the face of it then that in general there will be no such thing called potential energy, which has the property its derivatives are equal to the force. It's a law of physics that it's true. It's not something that you can derive from anything else. It's a law of physics obtained by experience, obtained by experiment, but really, really central. As we move along and as we go through classical mechanics, we'll find out how central it is. But for now, we will take it as a postulate that there exists a v of x so that the components of force are equal to, let's call it the gradient, or the partial derivatives along x. It's the same idea as it is in one dimension, that wherever you are, there's a force pointing along the direction where v decreases at the maximal rate, the steepest descent. You're standing on the side of a hill, and there's one direction which is the steepest descent. There's another direction where the hill doesn't vary in altitude. Perpendicular to that is a direction where the hill is maximally steep. That's called the direction of steepest descent. And the force points along the direction of steepest descent. That's what this equation says. And in fact, it's proportional to the, each component is proportional to the steepness along that particular direction. All right, from this, we can prove conservation of energy. Again, for only one, at the moment, we're dealing with only one particle. What do? We just do exactly the same thing. We put an x sub I dot squared and we sum over I. All right, what does that mean? That means that the kinetic energy is the sum of the components of is the square of the total, is 1/2 the mass times the square of the total velocity. This is just Pythagorean theorem. X sub I dot squared, that's the square of the total velocity, of the vector the total velocity. Sum over I. X dot squared plus Y dot squared plus Z dot squared, in other words. This is now called the kinetic energy. And V is still just one function of position. And this is still called the energy. Again, we now want to differentiate it with respect to time. What do we get? Well, first of all, we get exactly what we got before, but now summed over I. Do exactly the same trick. Differentiate x sub I dot squared. You get x sub I dot times x sub I double dot. The 2's cancel again. And that's what you're left with for the derivative of the kinetic energy. What about the potential energy? What's the derivative of the potential energy with respect to time? Well, it has a term for each direction. Each one of the components of direction might be varying. Each one of the components, x, y, and z of the particle may be varying. And the total time derivative of the potential energy is equal, simple calculus formula, the change in V if you move along the x direction or the x1 direction, let's call it x1, times the rate at which x1 is varying, plus the same thing for 2. The rate of change of V with respect to x2 times the x2. Let's just call it x2 dot. And so forth. Or, to use the I notation, x sub I dot. And this is also summed on I. Everything now in this equation is summed on I, both terms. And now we're finished. Because the equation, again, there's an x sub I dot. Let's take it outside the bracket. And look like what we have inside the bracket. Mass times acceleration minus force. Force being minus dv by dx. So again, it's the same derivation, just decorated with an index I, which gets summed over. So what's in the bracket here is 0. That's just Newton's equations. And the time derivative of the energy is equal to 0. All right, so again, in this case now, unlike the one-dimensional case, we did make a physical assumption. And we'll call that physical assumption a law of nature. What is it? It's energy conservation. I mean, you can think of it as energy conservation, or you can just think of it as forces are proportional to gradients or derivatives of a quantity called the potential energy. What happens if we have a lot of particles? Supposing we have a lot of particles, we can do exactly the same thing. For every particle, how do we describe a bunch of particles? We describe a bunch of particles by writing x1, now 1, 2, and 3, 1, 2, 3, 4, 5 stand for the particles, not for the directions. There's x1, y1, z1, that's the position of the first particle, x2, y2, z2, that's the position of the second particle, and so forth and so on. Let's take this whole column, all of them, and call them xi. the whole set of them, all of the coordinates of all the particles, let's label them xi. How many of them are altogether? Supposing there are n particles, how many xi's are there? 3n. One for each direction of space. Sorry, n for each direction of space. And we'll just call that xi. We can write down Newton's laws basically exactly the same way, but now we can introduce an mi over here. Now what does that mi mean? Different particles have different masses in general, okay? I'm actually allowing for the possibility that there is a different mass for each one of these 3n coordinates. Now, of course, what we expect the mass for the first particle to all be the same no matter which direction. We expect the masses for the second particle to all be the same as each other, independent of the direction. So we may not really have 3n different masses. We only have n different masses. But still, we can call the first mass here, we can call it, we can label the masses as if there was a separate mass for each direction and each particle. And then remember afterwards that, that the masses come in triplets. All right. First particle has all the same masses, regardless of direction. Second particle has all the direction. But in that, if we do that, then this becomes the equations for all of the particles and all of the directions of space. An xi for each direction and each particle, and a mass to go with it, and the force is equal to whatever it is equal to, number one. And number two, assume that all of the components of forces for all of the particles are proportional to the derivative of a potential energy, where the potential energy depends on all of the positions of all the particles, but the force on each particle in each direction is given by the derivative with respect to that particular coordinate. If we do that, then this argument is basically unchanged. And we find that there's energy conservation for the entire system. For any system of particles exerting forces, assuming the forces are governed by a potential energy. There are a word for forces which are governed by potential energies. They're called conservative. It's not a political description. It's that they conserve energy, that they're associated with energy conservation. Conservative forces like this, same exact derivation for any number of particles moving in any number of dimensions. The energy, the kinetic energy plus the potential. And the only thing we have to do is put an mi here. Kinetic energy, mi squared, x sub I dot squared. And that proves that from the assumption of conservative forces, we have conservation of energy. Potential and energy and kinetic energy just being exchanged back and forth as the particle moves in this landscape of rolling hills. Energy conservation. Let's come back now to that harmonic oscillator. We originally said let the mass and the spring constant equal 1. In that case, of course, the kinetic and potential, wait, go back a step. Yeah, what about the potential energy for a spring, for a particle moving on the end of a spring? Remember what the rule was? The force is equal to minus kx. Force is equal to minus kx for the spring. What's the potential energy? The potential energy is equal to k over 2 x squared. Why do I say that? We'll differentiate this with respect to x. Differentiating with respect to x, we get dv by dx, so just dv by dx, dv by dx is equal to kx. And minus dv by dx is minus kx. So we see that this is the right expression for the potential energy of the oscillator, proportional to the square of the displacement. Okay. What about the kinetic energy? The kinetic energy is 1/2 mv squared. So the total energy is 1/2 m x dot squared plus k over 2 x squared. Potential, kinetic. And if in fact we set the mass equal to 1 and k equal to 1 just for the purposes of comparing with the earlier illustration, we find out that the total energy is the sums of the squares of the velocity and the position. This is the origin of the fact that the particle moves on circular orbits, with this being x and this being x dot or p. All right, so we see that the circular motion moving along orbits like this was simply nothing but staying on orbits of constant energy. In fact, the energy increases quadratically as you move away from the center, and these orbits are nothing but the contours of constant potential energy. In general, for any particle moving in one dimension, it will always move on curves of constant x dot squared plus v of x. V of x may be more complicated. There may be a more complicated kind of v of x. It will move on the contours of constant energy. In the xp plane in phase space, it will move on the contours of constant energy. So that's energy conservation. And it's an example of the sort of thing we talked about the first lecture, when systems might have cycles that they cycle around on, and if there's more than one cycle, then there's a conserved energy, or conserved quantity. Okay, any questions about either momentum conservation or energy conservation? No, it doesn't look like we're going to get to the principle of least action tonight. Next time, we'll take up the principle of least action, which is another formulation of mechanics, a very general formulation of mechanics. And we'll get to Lagrangians and all sorts of interesting things, which will take us into more advanced aspects of mechanics. We'll get to Hamiltonians eventually. Conservation laws, generally. Angular momentum, all the good things. So we're set up for them. Any questions? Yes?
What's the relationship between these notes you're handing out and what you're doing up there?
I think it probably follows fairly close.
It looks like there's more up there than
I don't think so. I'm not, which notes are you talking about? Did you get some notes today in your email?
Yeah.
Was it the same? Was it the same as what I gave you last time? There's more, right? Yeah. I'll bet you I can find everything in there that's in here. And if I can't, I made a mistake and sent you the wrong thing. I don't think I did.
Where are the figures?
The figures haven't been made yet. Look. I'll tell you what, when the Department of Continuing Studies pays my check next month, I will put out the figures.
For more, please visit us at stanford.edu.